Welcome to The Explainer. Today, we're going to pull back the curtain on the internet. We're going to uncover the hidden orchestra of computers that has to work in perfect harmony every single time you click, swipe, or stream.
So let's kick things off with a question that I bet you've thought about, even if you didn't put it into words. How do these massive services like Netflix or Google handle millions of us all at once without just collapsing? The answer to that question reveals pretty much everything about how our modern digital world is built.
All right, so to really get how things work today, we've got to jump in a time machine and go way back. Because in the early days of the internet, everything was built on an idea that was beautifully simple and, as it turns out, dangerously fragile.
Picture this, the very early days of Facebook, back when it was just a thing at Harvard. The entire operation ran on one single server. That means one copy of all the data. Now, on one hand, this was great. It was so simple. A student makes a profile, it gets saved in one spot. Another student looks them up, the server knows exactly where to find it. But that simplicity was also its greatest weakness.
And yeah, that single server idea, it had three massive show-stopping headaches. First, any single glitch, a power cord gets kicked out, a hard drive fails, and poof, the entire site is gone for everyone. Then there's the scaling problem. You can only make one computer so fast before you basically hit the laws of physics. And finally, distance was a killer. If you were in Oxford trying to connect to a server in Harvard, the whole thing just felt painfully slow.
Okay, so if one super powerful computer just isn't going to cut it, what's the solution? Well, it's kind of obvious, right? You don't use one computer, you use thousands of them. And this simple idea is the bedrock of almost every single app you use today. And that brings us to this really cool concept called a distributed system. The magic here is right in the definition. It's a whole bunch of separate computers that work together so well they appear as one single, gigantic computer to you.
You know, the best way to think about it is like a group project at school. Instead of one person trying to do all the work and burning out, the tasks get divided up. Each person does their part, but they all have to coordinate to deliver one single final presentation.
And I mean, look at the difference here. It is night and day. Instead of one single point of failure, you get what's called fault tolerance. If one computer goes down, the others just pick up the slack. Instead of being limited, you can scale to millions, even billions of users. And because you can put computers closer to people all over the world, everything feels incredibly fast. Okay, but here's where the story takes a turn. Because in solving that massive scaling problem, the engineers accidentally created a brand new one. And honestly, this new problem is way, way harder to solve.
I mean, just think about it for a second. If you have copies of your data, your bank balance, your social media profile, on servers in New York, London, and Tokyo, how on earth do you guarantee that they all show the exact same information at the exact same time?
Well, this nightmare has a name, and in the world of computer science, it is an absolute monster. It's called consistency.
So what is data consistency? Put simply, it's just the principle that if you have multiple copies of something, all of those copies better be the same. Sounds simple, right? Well, it's not.
Okay, let's make this super clear. Imagine your bank balance is $100. You're in New York and you take out $10. So the New York server updates your balance to $90. But what about the server in London? For a split second, maybe longer, it still thinks you have $100. The system is literally in two states at once. For a social media like, that's a little annoying. For a bank, it's a catastrophe.
And this whole mess leads us to a fundamental dilemma, a huge trade-off that sits at the very heart of pretty much every big internet service out there. You have to choose. Do you want to be right or do you want to be fast? Because it is incredibly hard to be both at the same time.
So, to make sure the data is the same everywhere, these computers have to be constantly chatting. An update happens in the US, so it sends a message to a server in Europe. But then, the US server has to wait for Europe to message back and say, "Yep, got it." But what if that confirmation message just gets lost in the ether? The network has a hiccup. Now what? Is the update done? Who knows? The whole system is stuck in this state of uncertainty.
So this puts designers at a huge fork in the road. They have to make a choice. On one path, you have what's called strong consistency. This is the path of being perfectly correct all the time. The system will literally wait, no matter how long it takes, until every single copy is updated before it gives you the thumbs up. It's always right, but man, it can feel slow. Then there's the other path, high availability. This is the need for speed path. The system responds instantly and just kind of trusts that the other copies will get the memo in the background. It feels super fast, but you run the risk that for a moment, the data you're seeing is a little stale.
So, what do most systems do? Well, they can't really be all one or all the other, so they land on a clever compromise called eventual consistency. It's basically a promise. It says, hey, the data might not match right this second, but just give it a moment. It'll all sync up and become consistent eventually.
Okay, so consistency, availability, these trade-offs, why does any of this techie stuff actually matter to you? Well, because this completely abstract choice is quietly running your entire digital life. Every single day.
No, really, think about it. When you search on Google, you want those results right now. You don't really care if a web page that was published 2 seconds ago isn't there yet. That's a choice for high availability. Or Netflix, you want your movie to start playing instantly. That's way more important than knowing if a brand new show is added a millisecond ago. But your banking app? Oh, that's different. That has to be correct, period. So they choose strong consistency, even if it makes you wait an extra second or two for a transaction to go through.
So the crucial thing to remember is this. Next time you do anything online, tap an app, like a photo, stream a movie, remember that invisible orchestra. It's not one machine. It's thousands, all playing in harmony, constantly making these tiny trade-offs between being perfectly right and being unbelievably fast, just to make it all feel seamless to you.
So I want to leave you with a final thought. Pick your favorite app, any app. Now that you understand the trade-off, which path do you think its designers chose? Correctness or speed? And maybe more importantly, which one would you rather they choose for that app? Would you rather be perfectly correct or always fast?